Black Holes and Time Warps, Einstein's Outrageous Legacy. Prologue, a voyage among the holes, in which the reader, in a science fiction tale, encounters black holes and all their strange properties as best we understand them in the 1990s. Of all the conceptions of the human mind, from unicorns to gargoyles to the hydrogen bomb, the most fantastic, perhaps, is the black hole. A hole in space with the definite edge into which anything can fall and out of which nothing can escape. A hole with gravitational force so strong that even light is caught and held in its grip. A hole that curves space and warps time. Like unicorns and gargoyles, black holes seem more at home in the realms of science fiction and ancient myth than in the real universe. Nonetheless, well-tested laws of physics predict firmly that black holes exist. In our galaxy alone, there may be millions, but their darkness hides them from view. Astronomers have great difficulty finding them. Hades. Imagine yourself the owner and captain of a great spacecraft with computers, robots, and a crew of hundreds to do your bidding. You have been commissioned by the World Geographic Society to explore black holes in the distant reaches of interstellar space and radio back to Earth a description of your experiences. 6 years into its voyage, your starship is now decelerating into the vicinity of the black hole closest to Earth, a hole called Hades, near the star Vega. On your ship's video screen, you and your crew see evidence of the hole's presence. The atoms of gas that sparsely populate interstellar space, approximately 1 in each cubic centimeter, are being pulled by the hole's gravity. Figure P1. They stream toward the hole from all directions, slowly at great distances where gravity pulls them weakly, faster nearer the hole where gravity is stronger, and extremely fast, almost as fast as light, close to the hole where gravity is strongest. If something isn't done, your starship too will be sucked in. Quickly and carefully, your first mate, Chaos, maneuvers the ship out of its plunge and into a circular orbit, then shuts off the engines. As you coast around and around the hole, the centrifugal force of your circular motion holds your ship up against the hole's gravitational pull. Your ship is like a toy slingshot of your youth on the end of a whirling string. Pushed out by its centrifugal force and held in by the string's tension, which is like the hole's gravity. As the starship coasts, you and your crew prepare to explore the hole. At first, you explore passively. You use instrumented telescopes to study the electromagnetic waves, the radiation that the gas emits as it streams toward the hole. Far from the hole, the gas atoms are cool. just a few degrees above absolute zero. Being cool, they vibrate slowly, and their slow vibrations produce slowly oscillations, electromagnetic waves, which means waves with long distances from one crest to the next, long wavelengths. These are radio waves. See figure P2. Nearer the hole, where gravity has pulled the atoms into a faster stream, they collide with each other and heat up to several thousand degrees. The heat makes them vibrate more rapidly and emit more rapidly oscillating shorter wavelengths. Waves that you recognize as light of varied hues: red, orange, yellow, green, blue, violet. Figure P2. Much closer to the hole, where gravity is much stronger and the stream much faster, collisions heat the atoms to several million degrees, and they vibrate very fast, producing electromagnetic waves of very short wavelength, X-rays. Seeing those X-rays pour out of the hole's vicinity, you are reminded that it was by discovering and studying just such X-rays that astrophysics in 1972 identified the first black hole in distant space, Cygnus X1, 6,000 light years from Earth. Footnote 3, Chapter 8, page 26. Turning your telescopes still closer to the hole, you see gamma rays from atoms heated to still higher temperatures. Then, looming up at the center of this brilliant display, you see a large round sphere, absolutely black. It is the black hole, blotting out all the light, X-rays, and gamma rays from the atoms behind it. You watch a super hot atom stream into the black hole from all sides. Once inside the hole, hotter than ever, they must vibrate faster than ever and radiate more strongly than ever. But their radiation cannot escape the hole's intense gravity. Nothing can escape. That is why the hole looks black, pitch black. With your telescope, you examine the black sphere closely. It has an absolutely sharp edge. The whole surface, the location of no escape. Anything just above the surface with sufficient effort can escape from gravity's grip. A rocket can blast its way free. Particles, if fired upward fast enough, can escape. Light can escape. But just below the surface, gravity's grip is inexorable. Nothing can escape from in there, regardless of how hard it tries. Not rockets, not particles, not light, not radiation of any sort. They can never reach your orbiting starship. The whole surface, therefore, is likely the horizon on Earth, beyond which you cannot see. That is why it has been named the horizon of the black hole. I repeat, the whole surface, therefore, is like the horizon on Earth, beyond which you cannot see. That is why it has been named the horizon of the black hole. Your first mate, Caris, measures carefully the circumference of your starship's orbit. It is 1 million kilometers, about half the circumference of the moon's orbit around the Earth. She then looks out at the distant stars and watches them circle overhead as the ship moves. By timing their apparent motions, she infers that it takes 5 minutes and 46 seconds for the ship to encircle the hole once. This is the ship's orbital period. From the orbital period and circumference, you can now compute the mass of the hole. Your method of computation is the same as was used by Isaac Newton in 1685 to compute the mass of the Sun. The more massive the object, sun or hole, the stronger its gravitational pull, and therefore the faster must be orbiting a body, planet, or starship. Move to avoid being sucked in, and thus the shorter the body's orbital period must be. I repeat, the more massive the object, sun or hole, the stronger its gravitational pull, and therefore the faster must an orbiting body, planet or starship, move to avoid being sucked in, and thus the shorter the body's orbital period must be. By applying Newton's mathematical version of this gravitational law to your starship's orbit, you compute that the black hole Hades has a mass 10 times larger than that of the Sun, 10 solar masses. Footnote 7. Readers who want to compute properties of black holes over themselves will find the relevant formulas in notes at the end of the book. Page 27. You know that this hole was created long ago by the death of a star, a death in which the star, no longer able to resist the inward pull of its own gravity, imploded upon itself. You also know that when the star imploded, its mass did not change. The black hole Hades has the same mass today as its parent star had long ago, or almost the same. Hades' mass must actually be a little larger, augmented by the mass of everything that has fallen into the hole since it was born: interstellar gas, rocks, starships. You know all this because, before embarking on your voyage, you studied the fundamental laws of gravity, laws that were discovered in an approximate form by Isaac Newton in 1687 and were radically revised into a more accurate form by Albert Einstein in 1915. You learn that Einstein's gravitational laws, which are called general relativity, force black holes to behave in these ways as inexorably as they force a dropped stone to fall to earth. It is impossible for the stone to violate the laws of gravity and fall upward or hover in the air. And similarly, it is impossible for a black hole to evade the gravitational laws. The hole must be born when a star implodes upon itself. The hole's mass at birth must be the same as the star's, and each time something falls into the hole, its mass must grow. Footnote 10. For further discussion of the concept that the laws of physics force black holes and the solar system and the universe to behave in certain ways, see the last few paragraphs of chapter 1. Similarly, if the star is spinning as it implodes, then the newborn hole must also spin, and the hole's angular momentum, a precise measure of how fast it spins, must be the same as the star's. Before your voyage, you also studied the history of human understanding about black holes. Back in the 1970s, Brandon Carter, Stephen Hawking, Werner Israel, and others, using Einstein's general relativistic description of the laws of gravity, deduced that a black hole must be an exceedingly simple beast. All of the hole's properties, the strength of its gravitational pull, the amount by which it deflects the trajectories of starlight, the shape and size of its surface, and determined by just three numbers: the hole's mass, which you know now, the angular momentum of its spin, which you don't yet know, and its electrical charge. I repeat, all of the hole's properties, the strength of its gravitational pull, the amount by which it deflects the trajectories of light, the shape and size of its surface, are determined by just three numbers: the hole's mass, which you now know, the angular momentum of its spin, which you don't know yet, and its electrical charge. You are aware, moreover, that no hole in interstellar space can contain much electrical charge. If it did, it quickly would pull opposite charges from the interstellar gas into itself, thereby neutralizing its own charge. Page 28. As it spins, the hole should drag the space near itself into a swirling tornado-like motion relative to space far away, much as a spinning airplane propeller drags air near itself into motion, and the swirl of space should cause a swirl in the motion of anything near the hole. To learn the angular momentum of Hades, you therefore look for a tornado-like swirl in the stream of interstellar gas atoms as they fall into the hole. To your surprise, as they fall closer and closer to the hole, moving faster and faster, there is no sign at all of any swirl. Some atoms circle the hole clockwise as they fall, others circle it counterclockwise and occasionally collide with clockwise circling atoms, but on average, the atoms fall directly inward, directly downward, with no swirl. Your conclusion: this 10 solar mass black hole is hardly spinning at all. Its angular momentum is close to zero. Knowing the mass and angular momentum of the hole, and knowing that its electrical charge must be negligibly small, you can now compute, using general relativistic formulas, all of the properties that the hole should have: the strength of its gravitational pull, its corresponding power to deflect light, and the greatest interest, the shape and size of its horizon. If the hole were spinning, its horizon should have well delineated north and south poles. The poles about which it spins and about which falling atoms swirl. It would have a well delineated equator halfway between the poles, and the centrifugal force of the horizon spin would make its equator bulge out, just as the equator of the spinning Earth bulged a bit. Hades spins hardly at all, and thus must have hardly any equatorial bulge. Its horizon must be forced by the laws of gravity into an almost precisely spherical shape. That is just how it looks through your telescope. As for size, the laws of physics, as described by general relativity, insist that the more massive the whole is, the larger must be its horizon. The horizon's circumference, in fact, must be 18.5 kilometers multiplied by the mass of the whole in units of the sun's mass. Footnote 15, Chapter 3. The quantity 18.5 kilometers, which will appear many times in this book, is 4p, that is 12.56633706 times Newton's gravitational constant times the mass of the sun divided by the square of the speed of light. I repeat, the quantity 18.5 kilometers, which will appear many times in this book, is 4p, that is 12.56633706 times Newton's gravitation constant times the mass of the sun divided by the square of the speed of light. For this and other useful formulas describing black holes, see the notes of this chapter. Since your orbital measurements have told you that the whole weighs 10 times as much as the sun, its horizon circumference must be 18.5 times 10, 185 kilometers, about the same as Los Angeles. With your telescopes, you carefully measure the circumference, 185 kilometers, perfect agreement with the general relativistic formula. This horizon circumference is minuscule compared to your starship's 1 million-kilometer orbit. And squeezed into that tiny circumference is a mass 10 times larger than that of the sun. If the whole were a solid body squeezed into such a small circumference, its average density would be 200 million, 2 times 10 power to 8 tons per cubic meter. 2 times 10 power to 14 times more dense than water. But the whole is not a solid body. General relativity insists that the 10 solar masses of stellar matter, which created the whole by imploding long ago, are now concentrated at the whole's very center, concentrated into a minuscule region of space called a singularity. That singularity, roughly 10 powered to minus 33 centimeter in size, 100 billion times smaller than an atomic nucleus, should be surrounded by pure emptiness. Aside from the tenuous interstellar gas that is falling inward now and the radiation the gas emits. There should be near emptiness from the singularity out to the horizon, and near emptiness from the horizon out to your starship. Page 13. The singularity and the stellar matter locked up in it are hidden by the hole's horizon. However long you may wait, the locked up matter can never re-emerge. The hole's gravity prevents it, nor can the locked up matter ever send you information, not by radio waves or light or X-rays. For all practical purposes, it is completely gone from our universe. The only thing left behind is its intense gravitational pull, a pull that is the same on your 1 million kilometer orbit today as before the star imploded to form the black hole, but a pull so strong at and inside the horizon that nothing there can resist it. What is the distance from the horizon to the singularity? You ask yourself. You choose not to measure it, of course. Such a measurement would be suicidal. You could never escape back out of the horizon to report your result to the World Geographic Society. Since the singularity is so small, 10 powered to minus 33 centimeter, and is at the precise center of the whole, the distance from singularity to the horizon should be equal to the horizon's radius. You are tempted to calculate this radius by a standard method of dividing the circumference by 2 pi, 6.283185307. However, in your studies on Earth, you were warned not to believe such a calculation. The hole's enormous gravitational pull completely distorts the geometry of space inside near the hole. In much the same manner as an extremely heavy rock placed on a sheet of rubber distorts the sheet's geometry, and as a result, the horizon's radius is not equal to its circumference divided by 2 pi. Never mind, you say to yourself. Lobachevsky, Riemann, and other great mathematicians have taught us how to calculate the properties of circles when space is curved, and Einstein has incorporated those calculations into his general relativistic description of the laws of gravity. I can use these curved space formulas to compute the horizon's radius. But then you remember from your studies on Earth that although a black hole's mass and angular momentum determine all the properties of the hole's horizon and exterior, they do not determine its interior. General relativity insists that the interior near the singularity should be chaotic and violently non-spherical, much like the tip of the rubber sheet in figure P3. If the heavy rock in it is jagged and is bouncing up and down wildly. Moreover, the chaotic nature of the hole's core will depend not only on the hole's mass and angular momentum, but also on the details of the stellar implosion by which the hole was born, and the details of the subsequent inflow of interstellar gas, details that you do not know. So what, you say to yourself, Whatever may be its structure, the chaotic core must have a circumference far smaller than a centimeter. Thus, I will make only a tiny error if I ignore it when computing the horizon's radius. But then you remember that the space can be so extremely warped near the singularity that the chaotic region might be millions of kilometers in radius, though only a fraction of a centimeter in circumference. Just as the rock in figure P3. If heavy enough, can drive the chaotic tip of the rubber sheet exceedingly far downward while leaving the circumference of the chaotic region extremely small. The errors in your calculated radius could not be enormous. The horizon's radius is simply not computable from the meager information you possess, the hole's mass, and its angular momentum. Page 32. Abandoning your musings about the hole's interior, you prepare to explore the vicinity of its horizons. Not wanting to risk human life, you ask a rocket-endowed 10-centimeter tall robot named Arnold to do the exploration for you and transmit the results back to your starship. Arnold has simple instructions. He must first blast his rocket engines just enough to hold the circular motion that he has shared with the starship, and then he must turn his engines off and let the hole's gravity pull him directly downward. As he falls, Arnold must transmit a brilliant green laser beam back to the starship, and on the beam's electromagnetic oscillations he must encode information about the distance he has fallen and the status of his electronic systems, much as a radio station encodes a newscast on the radio waves it transmits. Back into the starship, your crew will receive the laser beam, and Cares will decode it to get the distance and system information. She will also measure the beam's wavelength, or equivalently, its color. The wavelength is important. It tells you how fast Arnold is moving. As he moves faster and faster away from the starship, the green beam he transmits gets Doppler shifted as received at the ship to longer and longer wavelengths. That is, it gets more and more red. There is an additional shift to the red caused by the beam's struggle against the hole's gravitational pull. When computing Arnold's speed, Cares must correct her calculations for this gravitational redshift. And so the experiment begins. Arnold blasts his way out of the orbit and into an falling trajectory. As he begins to fall, Cares starts a clock to time the arrival of his laser signals. When 10 seconds have passed, the decoded laser signal reports that all his systems are functioning well and that he has already fallen a distance of 2,630 kilometers. From the color of the laser light, Cares computes that he is now moving inward with a speed of 530 kilometers per second. When the ticking clock has reached 20 seconds, his speed has doubled to 1060 kilometers per second, and his distance of fall has quadrupled to 10,500 kilometers. The clock ticks on. At 60 seconds, his speed is 9,700 kilometers per second, and he has fallen 135,000 kilometers, 5/6 of the way to the horizon. You know, you now must pay very close attention. The next few seconds will be crucial. So Cortes turns on a high-speed recording system to collect all details of incoming data. At 61 seconds, Arnold reports all systems still functioning normally. The horizon is 14,000 kilometers below him, and he is falling toward it at 13,000 kilometers per second. At 61.7 seconds, all is still well. 1,700 kilometers more to go. Speed 39,000 kilometers per second, or about 1/10 of the speed of light. Laser color beginning to change rapidly. In the next 1/10 of 1 second, you watch in amazement as the laser color zooms through the electromagnetic spectrum, from green to red to infrared to microwave to radio wave to... By 61.8 seconds, it is all over. The laser beam is completely gone. Arnold has reached the speed of light and disappeared into the horizon. And in that last tenth of a second, just before the beam winked out, Arnold was happily reporting, "All systems go, all systems go, horizon approaching, all systems go, all systems go." As your excitement subsides, you examine the recorded data. There, you find the full details of the shifting laser wavelength. You see that as Arnold fell, the wavelength of the laser signal increased very slowly at first, and faster and faster. But surprisingly, after the wavelength had quadrupled, its rate of doubling became nearly constant. Thereafter, the wavelength doubled every 0.00014 seconds. After 33 doublings, 0.0046 seconds, the wavelength reached 4 kilometers, the limit of your recording system's capabilities. Presumably, the wavelength kept right on doubling thereafter, since it takes an infinite number of doublings for the wavelengths to become infinite. Exceedingly faint, exceedingly long wavelength signals might still be emerging from near the horizon. Does this mean that Arnold has not yet crossed the horizon and never will? No, not at all. Those last forever doubling signals take forever long to climb out of the hole's gravitational grip. Arnold flew through the horizon, moving at the speed of light many minutes ago. The weak remaining signals keep coming out only because their travel time is so long. They are relics of the past. After many hours of studying data from Arnold's fall, and after a long sleep to reinvigorate yourself, you embark on the next stage of exploration. This time, you yourself will probe the horizon's vicinity, but you will do it much more cautiously than did Arnold. Bidding farewell to your crew, you climb into a space capsule and drop out of the belly of the starship and into a circular orbit alongside it. Then blast your rocket engines ever so gently to slow your orbital motion a bit. This reduces slightly the centrifugal force that holds your capsule up, and the hole's gravity then pulls you into a slightly smaller coasting circular orbit. As you again gently blast your engines, your circular orbit again gently shrinks. Your goal by this gentle, safe inward spiral is to research a circular orbit just above the horizon, an orbit with circumference just 1.0001 times larger than that of the horizon itself. There you can explore most of the horizon's properties but still escape its fatal grip. As your orbit slowly shrinks, however, something strange starts to happen. Already at a 100,000 kilometer circumference, you feel it. Floating inside the capsule, with your feet toward the hole and your head toward the stars, you feel a weak downward tug on your feet, an upward tug on your head. You are being stretched like a piece of taffy candy, but gently. The cause, you realize, is the hole's gravity. Your feet are closer to the hole than your head, so the hole pulls on them harder than on your head. The same was true, of course, when you used to stand on the earth, but the head to foot difference on earth was so minuscule, less than one part in a million, that you never noticed it. By contrast, as you float in your capsule at a circumference of 100,000 kilometers, the head to foot difference is 1/8 of an Earth gravity. At the center of your body, the centrifugal force of your orbital motion precisely counteracts the hole's pull. It is as though gravity did not exist. You float freely, but at your feet, the stronger gravity pulls down with an added 1/16th g, and at your head, the weaker gravity allows the centrifugal force to push up with an added 1/16th g. Bemused, you continue your inward spiral, but your bemusement quickly changes to worry. As your orbit grows smaller, the forces on your head and feet grow larger. At a circumference of 80,000 kilometers, the difference is a 1/4 g stretching force. At 50,000 kilometers, it is a full Earth gravity stretch. At 30,000 kilometers, it is 4 Earth gravities. Gritting your teeth in pain as your head and feet are pulled apart, you continue on into 20,000 kilometers and a 15 g stretching force. More into a tight ball. More than this you cannot stand. You try to solve the problem by rolling up into a tight ball so your head and feet will be closer together and the difference in forces smaller. But the forces are so strong that they will not let you roll up. They snap your back out into a radial head to foot stretch. If your capsule spirals is much farther, your body will give way. You will be torn apart. There is no hope of reaching your horizon's vicinity. Frustrated and in enormous pain, you hold your capsule's descent, turn it around, and start carefully, gently blasting your way back up through circular coasting orbits of larger and larger circumference, and then into the belly of the starship. Entering the captain's chamber, you vent your frustrations on the ship's master computer, Dawn. Tiki, tiki, she says soothingly, drawing words from the ancient Russian language. I know you are upset, but it is really your own fault. You were told about those head to foot forces in your training, remember? They are the same forces as produce the tides on the oceans of the earth. Thinking back to your training, you recall that the oceans on the side of the earth nearest to the moon are pulled most strongly by the moon's gravity and thus bulge out toward the moon. The oceans on the opposite side of the Earth are pulled most weakly and thus bulge out away from the moon. The result is two oceanic bulges, and as the Earth turns, those bulges show up as two high tides every 24 hours. In honor of those tides, you recall the head to foot gravitational force that you felt is called a tidal force. You also recall that Einstein's general relativity describes this tidal force as due to a curvature of space and orbit of time, or in Einstein's language, a curvature of space-time. Tidal forces and space-time distortions go hand in hand, one always accompanies the other, though in the case of ocean tides, the distortion of space-time is so tiny that it can be measured only with extremely precise instruments. But what about Arnold? Why was he so blithely immune to the whole tidal force? For two reasons, Don explains. First, because he was much smaller than you, only 10 centimeters high, and the tidal force, being the difference between the gravitational pulls at his head and his feet, was correspondingly smaller. And second, because he was made of a super strong titanium alloy that could withstand the stretching force far better than your bones and flesh. Then, with horror, you realize that as he fell through the horizon and on in toward the singularity, Arnold must have felt the tidal force rise up in strength until even his super strong titanium body could not resist it. Less than 0.0002 seconds after crossing the horizon, his disintegrating, stretching body must have neared the whole central singularity. Page 36. There, you recall from your study of general relativity back on Earth, the whole tidal forces must come to life, dancing a chaotic dance, stretching Arnold's remains first in this direction, then in that, then in another, faster and faster, stronger and stronger, until even the individual atoms of which he was made are distorted beyond all recognition. That, in fact, is one essence of the singularity. It is a region where chaotically oscillating space and curvature creates enormous chaotic tidal forces. Musing over the history of black hole research, you recall that in 1965 the British physicist Roger Penrose used general relativity's description of the laws of physics to prove that a singularity must reside inside every black hole. And in 1969, the Russian Troika of Lifshitz, Kalatnikov, and Belinsky used it to deduce that very near the singularity, tidal gravity must oscillate chaotically, like taffy being pulled first this way and then that by a mechanical taffy pulling machine. Those were the golden years of theoretical black hole research, 1960s and 1970s. But because the physicists of those golden years were not clever enough at solving Einstein's general relativity equations, one key feature of black hole behavior eluded them. They could only conjecture that whenever an imploding star creates a singularity, it must also create a surrounding horizon that hides the singularity from view. A singularity can never be created naked. for all the universe to see. Penrose called this the conjecture of cosmic censorship, since, if correct, it would censor all experimental information about singularities. One could never do experiments to test one's theoretical understanding of singularities unless one were willing to pay the price of entering a black hole, dying while making the measurements, and not being able to transmit the results back out to the hole as a memorial to one's efforts. Although Dame Abigail Lehman in 2023 finally resolved the issue of whether cosmic censorship is true or not, the resolution is irrelevant to you now. The only singularities charted in your ship's atlases are those inside black holes, and you refuse to pay the price of death to explore them. Fortunately, outside but near black hole horizon, there are many phenomena to explore. You are determined to experience those phenomena firsthand and report back to the World Geographic Society, but you cannot experience them near Ad's horizon. Page 37. The tidal force there is too great. You must explore, instead, a black hole with weaker tidal forces. General relativity predicts, Dawn reminds you, that as a hole grows more massive, the tidal forces at and above its horizon grow weaker. This seemingly paradoxical behavior has a simple origin. The tidal force is proportional to the hole's mass divided by the cube of its circumference. So, as the mass grows and the horizon circumference grows proportionally, the near horizon tidal force actually decreases. For a hole weighing 1,000,000 solar masses, that is 100,000 times more massive than others, the horizon will be 100,000 times larger, and the tidal force there will be 10 billion times weaker. That would be comfortable, no pain at all. So you begin making plans for the next leg of your voyage, a journey to the nearest million solar mass hole listed in Schechter's Black Hole Atlas, a hole called Sagittario at the center of our Milky Way galaxy, 30,100 light years away. Several days later, your crew transmits back to Earth a detailed description of your Athens explorations, including motion pictures of you being stretched by tidal forces and pictures of atoms falling into the hole. The description will require 26 years to cover the 20 light year distance to Earth. And when it finally arrives, it will be published with great fanfare by the World Geographic Society. In their transmission, the crew describe your plan for a voyage to the center of the Milky Way. Your Starship rocket engines will blast all the way with a 1G acceleration so that you and your crew can experience a comfortable 1 Earth gravity force inside the starship. The ship will accelerate toward the galactic center for half the journey, and then it will rotate 180 degrees and decelerate at 1G for the second half. The entire trip of 30,100 light years distance will require 30,102 years as measured on Earth, but as measured on the starship, It will require only 20 years. In accordance with Einstein's laws of special relativity, your ship's high speed will cause time, as measured on your ship, to dilate, and this time dilation, or time warp, in effect, will make the starship behave like a time machine, projecting you far into the Earth's future while you age only a modest amount. You explain to the World Geographic Society that your next transmission will come from the vicinity of the galactic center after you have explored its million solar mass hole, Sagittario. Members of the society must go into deep freeze hibernation for 60,186 years if they wish to live to receive your transmission. 30,102 minus 26 equals 30,076 years from the time they receive your message until you reach the galactic center, plus 30,110 years while your next transmission travels from the galactic center to the Earth. Page 38. Sagittario. After a 20-year voyage, as measured in the starship time, your ship decelerates into the Milky Way center. There, in the distance, you see a rich mixture of gas and dust flowing inward from all directions toward an enormous black hole. Cares adjusts the rocket blast to bring the starship into coasting circular orbit well above the horizon. By measuring the circumference and period of your orbit and plugging the results into Newton's formula, you determine the mass of the hole. It is 1,000,000 times the mass of the Sun, just as claimed in Schechter's Black Hole Atlas. From the absence of any tornado-like swirl in the inflowing gas and dust, you infer that the hole is not spinning much. Its horizon, therefore, must be spherical, and its circumference must be 18.5 million kilometers, 8 times larger than the Moon's orbit around the Earth. After further scrutiny of the infalling gas, you prepare to descend toward the horizon. For safety, Cares sets up a laser communication link between your space capsule and your starship's master computer, Dawn. You then drop out of the belly of the starship, turn your capsule so its jets point in the direction of your circling orbital motion and start blasting gently to slow your orbital motion and drive yourself into a gentle inward-downward spiral from one coasting circular orbit to another. All goes as expected until you reach an orbit of circumference 55 million kilometers, just 3 times the circumference of the horizon. There, the gentle blast of your rocket engine, instead of driving you into a slightly tighter circular orbit, sends you into a suicidal plunge in toward the horizon. In panic, you rotate your capsule and blast with great force to move back into an orbit just outside 55 kilometers. 55 million kilometers. What the hell went wrong? You asked Dawn by laser link. Ticky, tick, she replies soothingly. You planned your orbit using Newton's description of the laws of gravity, but Newton's description is only an approximation to the true gravitational laws that govern the universe. It is an excellent approximation far from the horizon, but bad near the horizon. Much more accurate is Einstein's general relativistic description. It agrees to enormous precision with the true laws of gravity near the horizon, and it predicts that as you near the horizon, the pull of gravity becomes stronger than Newton ever expected. To remain in a circular orbit with this strengthened gravity, counterbalanced by the centrifugal force, you must strengthen your centrifugal force, which means you must increase your orbital speed around the black hole. As you descend through the three horizon circumferences, you must rotate your capsule around and start blasting yourself forward, because instead you kept lusting backward, slowing your motion. Gravity overwhelmed your centrifugal force as you passed through three horizon circumferences and hurled you inward. Damn that Dawn, you think to yourself. She always answers my questions, but she never volunteers crucial information. She never warns me when I'm going wrong. You know the reason, of course. Human life would lose its zest and richness if computers were permitted to give warning whenever a mistake was being made. Back in 2032, the World Council passed a law that a Hobson block preventing such warnings must be embedded in all computers. As much as she might wish, Dawn cannot bypass her Hobson block. Suppressing your exasperation, you rotate your capsule and being a careful sequence of forward blast, inward spiral, coast, forward blast, inward spiral, coast, forward blast, inward spiral, coast, which makes you from three horizon circumferences to 2.5 to 2 to 1.6 to 1.55 to 1.51 to 1.505 to 1.101 to what frustration! The more times you blast and the faster your resulting coasting, circular motion, the smaller becomes your orbit. But as your coasting speed approaches the speed of light, your orbit only approaches 1.5 horizon circumference. Since you can't move faster than light, there is no hope of getting close to the horizon itself by this method. Again, you appeal to Dawn for help, and again she soothes you and explains. Inside 1.5 horizon circumferences, there are no circular orbits at all. Gravity's pull there is so strong that it cannot be counteracted by any centrifugal forces, not even if one coasts around and around the hole at the speed of light. If you want to go closer, Dawn says, you must abandon your circular coasting orbit and instead descend directly toward the horizon, with your rockets blasting downward to keep you from falling catastrophically. The force of your rockets will support you against the hole's gravity. As you slowly descend and then hover just above the horizon, like an astronaut hovering and blasting rockets just above the moon's surface. Having learned some caution by now, you ask Dawn for advice about the consequences of such a strong, steady rocket blast. You explain that you wish to hover at a location 1.0001 horizon circumferences, where most of the effects of the horizon can be experienced, but from which you can't escape. If you support your capsule there by a steady rocket blast, how much acceleration force will you feel? 150 million Earth gravities, Dawn replies gently. Deeply discouraged, you blast and spiral your way back up into the belly of the starship. After a long sleep, followed by 5 hours of calculations with general relativist black hole formulas, 3 hours of plowing through Shakespeare's Black Hole Atlas, and an hour of consultation with your crew. You formulate the plan for the next leg of your voyage. Your crew then transmit to the World Geographic Society, under the optimistic assumption that it still exists, an account of your experiences with Sagittaria. At the end of the retransmission, your crew describe your plan. Your calculations show that the larger the hull, the weaker the rocket blast you will need to support yourself, hovering at 1.0001 horizon circumferences. For a painful but bearable 10 with gravity blast, the hull must be 15 trillion solar masses. That is 15 times 10 power to 12. Nearest such hull is the one called Gargantua, far outside the 100,000 light-year confines of your own Milky Way galaxy, and far outside the 100 million light-year Virgo cluster of galaxies, around which our Milky Way orbits. In fact, it is near the quasar 3C273, 2 billion light-years from the Milky Way and 10% of the distance to the edge of the observable part of the universe. The plan, your crew explained in their transmission, is a voyage to Gargantua, using the usual 1g acceleration for the first half of the trip and 1g deceleration for the second half. The voyage will require 2 billion years as measured on Earth, but thanks to the speed-induced warpage of time, only 42 years as measured by you and your crew in the starship. If the members of the World Geographic Society are not willing to chance a 4 billion year deep freeze hibernation, 2 billion years for the starship to reach Gargantua, and 2 billion years for its transmission to return to Earth, then they will have to forego receiving your next transmission. Page 41. Gargantua.